the unit 4 logic gates. So that's, if you look back, this is the basis for deciding electronic circuits, right? So all the electronic circuits, if you boil down how they have built, they uses very basic gates. So all the electronic components, especially digital electronics, you can see they build on top of what we call the basic logic gates, right? So they are the basic building blocks, right? So all the logical conditions, it uses what we call the binary values. So in this lesson, we will discuss in detail how we can come up with a small circuit, right, based on these logic gates. So in the first part, we look at the very basic logic gates. That means AND gate, OR gate, and NOT gate. So they are called basic logic gates. And the others actually been, built using combining these gates, which we call combination logic gates. So when it comes to logic gates, we can talk about two types as basic logic gates as well as combination logic gates. We'll start with the basic logic gates, right? And under basic logic gates, you can see we said there are three basic logic gates. So that's where we are going to start: AND gate, OR gate, and NOT gate. So let's start with AND gate first, right? So AND gate means, to demonstrate this one, let me come up with a small circuit, right? So in this circuit, we are going to have two switches and a bulb and a battery, right? And we connect the two switches in series. Let's see, right? So let's see the circuit. So we will have two switches, switch A, switch B, right? Two switches connected in series. And then we have bulb Q, and then there's a battery. Now what will happen? Now, if you take A, you have two states. If you take B, B also you have two states, right? B also you have two states, and then we have Q bulb, right? Now bulb also you have two states, switch on and switch off, right? Bulb will switch on and bulb will switch off. Everything is binary, right? Now if you look at how this circuit works, now if you close switch A, still bulb will not switch on because B is open. If B is only closed, then again Q is switched off, right? When both A and B close, Q is switch on, right? So to bulb in switch on position, both switches A and B should be closed, right? Now this we can interesting, right? So when both switches A and B are closed, then we know the bulb is Q is switch on, right? So that's all need to remember. And in all the other cases, that means when A is open, B is open, A is open, B is closed, then A is open, B is closed, right? All the other cases, Q will be switched off. Right, now I hope with that one, we got some idea how exactly this will work, right? So which means when we want to get the Q in switch on position, both switches A and B should be closed. Right. Now let's look at the different states. So if you look at switch A, I told you you have open and closed. Then switch B also you have open and closed. Then bulb Q, you have switch off and switch on. Right. So that means we can represent this as binary. So open means we can say 0. Close means it's 1. Similarly, bulb also we have two states, right? Q, switch off, then we can represent as 0. Switch on, we can represent as 1. So in the circuit A, B, and Q, how it works, we can put into, put into a table, right? So that's exactly what we are going to do. So we can put A, B, right? So let's start with looking at how AB works. Now, if you put A, B, and Q, right? Now we can say when A is open, B is open, Q, what will happen? Switch off. When A is open, B is closed, then Q is still switched off. Then the next one is, then A is closed, B is open, is still off. But when both A, B, Q is switched on. So if you put a table, we can put it like this, right? Open, open, switched off. Open, close, switched off. Close, open, switched off. Close, close, switched off. But remember we were discussing, if you can put this using binary, because we said when you say open, we can represent using 0. When A is closed, we can represent using 1. So if you put this combination, how exactly the circuit will work? Now in this table, we try to exactly represent how the circuit works. So when you put in binary, right, that we will call truth table. So truth table represent exactly how the gates works, right? So in our case, we will see when you put down everything in zeros and one, right? It will be the truth table for the AND logic gate. So if I put ones and zeros, you will see, right? If I put A, B, and Q, now when you say open, we put 0. B open is 0. A open is 0. Close is 1. Close is 1. Open is 0. Close, close, we have 1 and 1. So if you look at the output of Q, then we can represent Q as switched off, switched off, switched off. That means 0, 0, 0. And finally, it's switched 1. So what you need to remember about the AND logic gate is when both A and B is 1, then Q is 1. And all the other cases, Q will be 0. Right? So the output of AND gate is 1 when all the inputs are 1. Right. Okay. So let's take down this. So if you look at in the truth table, you will see that the output Q is always the multiplication of A and B. Q is equals to multiplying AB together, because 0 and 0, it will be 0. 0, 1, it will be 0. 1, 0, again 0. Right? 1 and 1, it will be 1. So this means A dot B, we will say A dot B, but actually it's A and B, right? So we can put down the symbol now for the logic gate and logic gate. And when you draw it, so you draw like a line, this one, and this is like a half circle, right? You'll have, this is a straight line, then this is a half circle. And then in our case, we were discussing two inputs. The inputs are A and B, and this is representing output. Output Q, we can say it as a multiplication of A, B together. Right. So, right. So I want you to try this alone. I want you to construct a truth table for 3 input truth table, right? That means using ones and zeros. And then I want to draw the symbol. Okay. So when we have 3 input AND gate, let's assume that the inputs are A, B, and C. And the Q, yes. So you have to do it as same as before, right? So what you need to remember is what is ABC. Now, if you look at this, we have 3 inputs, right? So that means how many possible combinations are there if you have 3 inputs? So when you have 3 inputs, then you should have 8 possible combinations. So the first one is 0, 0, 0. Then 0, 0, 1. Then 0, 1, 0. Then you have 0, 1, 1. So you see there's a pattern. So in C, you will say it's always changes as 0, 1, 0, 1. Then with B, you have 2 zeros and 2 ones. Now A, you have 4 zeros, right? Which means next one. What is the next one then? We have 1, 0, 0. Next, 1, 0, 1. Then 1, 1, 0. Then 1, 1, 1. Okay, now I want you to identify what Q is, right? So basically we know Q should be the multiplication of ABC together. So if you look at the outputs, when 0, 0, 0, it will be 0, 0, 0, 1, again 0, 0, 1, 0, again 0, 0, 1, 1, 0, 1, 0, 0, 0, multiplication 0, 0, and finally it should be 1, right? Now the second part is you need to draw the symbol. The symbol is the same as previous one. So you will have that shape, and then you will have 3 inputs, and we will name it as A, B, C. And the output, we can say it's Q, right? So in this particular case, we are going to start with O gate. O gate is slightly different from what we have seen earlier, right? Earlier, we had 2 switches. If you look at the same example, to represent the O gate, but we will get the 2 switches in parallel, right? So basically, we will have switch A, then we will have switch B, right? And then that means the 2 switches are in parallel, and then we'll connect Q, right? We'll connect Q, the circuit, and then we have battery. So the circuit looks like this. So in this particular case, now you will see how the circuit Q works. So now what will happen? We have 2 states here, open and close. Here also we have open and close. So here we have 2 states, switch off and switch on, right? Now, if you look at how exactly this will work, right? When either A or B close, in this particular case. If this closes, then it closed loop, Q will be switched on. If only B closes, then that will create another closed loop, Q is on. When both A, B close, that again Q is on. So which means when either switch A or B or both A, B are closed, then we can say the bulb Q is switched on. So like in previous case, if you tabulate this, let's put up a table and try to represent input and outputs. So it will be like this. So we know that A and B. So we will have open and open, open and close and open, and close, all possible combinations. So when A is open, B is open, that means this situation Q is switched off. When A is open and B is closed, so this is closed, so that means there's a loop, closed loop here. So again switch on. When only B is when A is closed, so this is closed, then there's a closed loop through switch A, which means the bulb Q is switched on. When both are closed, again it is the closed loop, so we will have switched on, right? So this is basically how OR gate works. So we try to explain how OR gate works using the circuit given to you. So we discussed earlier, like when you want to put the all possible combinations in binary form, it is called truth table. So we can draw truth table for OR gate, right? So we have three inputs, two inputs and one output Q. And we know that when A and B, right? So we have 0, 0, that means close, close. Then 0, 1, close, open. Then open, the closed and open. Sorry, earlier it was open, 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 close, close, open, close, close. Right. So either one of them is closed, then the output is Q. Right. So when both A and B is 0 only, Q is 0. So if you look at this, how this OR gate works, we can summarize the output of OR gate is 1 when one of the input is 1. So that's what you need to remember. Earlier, previously for AND gate, we said when both inputs are 1 only, you will get the output 1. So here output is 1 when one of the input is 1. So that's all you need to remember. So which means we can write down the expression. So for example, here, if you look closely, right? So try to add these to AB. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1, 1 plus 1, again this is binary, and this is plus means representing O, that means both AB close, so that is 1. So simply we can represent Q as a mathematical expression as A plus B. So when you say A plus B, actually it represents A or B. We know that it's not exactly the addition, but we will say Boolean addition, right? So when it comes to Boolean, addition, remember 1 plus 1 is 1, right? So it's slightly different from what we have learned in maths, because you can have only 0 and 1, right? So let's look at the symbol. Now to represent the symbol, right? Symbol for OR gate, basically you start the curved line and then like a triangle, right? So you put two lines to connect it, curved lines, right? And then we can have the inputs, the two inputs we said, and one output. We will have A, inputs B, and then we have Q. And we said we can write down Q is equal to A plus B, right? So we can represent a symbol for OR gate like this. So curved line, you start with the curved line. So all the three lines are curved line here when you're representing. So there's a curved line. and two curved lines to connect to one single point here. Then you have two inputs we represent at A and B. The output we can say Q. Q is equal to A plus B. We'll do a exercise on 3-input OR gate, right? So I want you to construct a truth table for 3-input OR gate, and then I need you to draw the symbol. So in this particular case, what you need to remember is we have 3 inputs, right? So that is A, B, C, and then we have Q output, right? Now, when you have 3 inputs, we know that there are 8 possible combinations as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So we need to find out what Q is. Okay, let's start. Now remember, what you need to remember is Q is equal to addition of A, B, C together, right? That means when you add 0, 0, 0, that means 0 plus 0 plus 0. So that should be 0. But in all the other cases, it should be 1, isn't it? Because the second one, if you look at it, yes, you have 0, 0, and 1. That means 0 plus 0 plus 1. That is 1. 0, 1, 0. That means 0 plus 1 plus 0. It's 1. The next one, you have 0 plus 1 plus 1. Remember, 1 plus 1 in binary, it should be 1 because it's O, right? And then 1 plus 0 plus 0, it's 1. 1, 0, 1, 1. 1, 1, 0, it's 1. 1, 1, 1, again 1. You see? So O means except all the inputs are 0, right? All the other cases output will be 1. Okay, so that's all you need to remember, right? Now let's look at the symbol as well. So if you want to draw the symbol, it will be the same as earlier, the same shape, but only difference is you have 3 inputs A, B, C. The output is Q, and we know that Q is A plus B plus C. So in this one, we will look at how NOT gate works. Like in previous case, we will make use of a small circuit, right? So first of all, let's look at this circuit. Now, what do you think about the circuit, right? We have a resistor R, and then we have a Q bulb and a battery, right? So when you have a resistor and a bulb and a battery, yes, it's a closed loop, right? Now, depend on the resistance, the amount of current go through the bulb will vary. Bulb, this will be switched on, isn't it? Yes. Now, we are going to connect another switch in between like this. You put a switch, right? Let me say this is A. Now, this is open, right? So when A is open, what will happen? There's a closed loop through this one, through R, through the bulb. And then what will happen? The bulb is off, isn't it? Bulb is off. Why? Because this will go through this. Once there's a switch connects in, things will slightly vary. When it open, as I told you earlier, the current flow through the bulb Q and this will switch off. Then when you close this one, things have changed because when current comes through this resistor, then there are 2 paths to take, either through A or Q, right? You have 2 paths. So most easiest path is A, because there's no resistance here. If there's a bulb will have a small resistance, because you take this easy path, isn't it? So the current flow through A, and there's no current through bulb Q. So which means, yes, but Q will be switch off. So we can say that when switch A is open, the bulb is Q is switched on. When A is closed, the bulb Q is switched off. So which means the NOT gate always provide the complement. So when we say A is open, that means when A is 0, Q is switched on, that means 1. So input is 0, output is 1. When A is closed, then bulb Q is switched off. Closed means A is 1, Q is 0. It is, we call it's a complement. The complement of 0 is 1, and the complement of 1 is also 0. That means the opposite value. So the complement value we say, right? Right. Now the next thing is, if you want to develop the truth table for NOT gate, is simple, because we will have only one input. So which means we have a table with one input and one output. When A is 0, then Q is 1. When Q is 1, sorry, A is 1, then Q is 0. So we said it's always a complement, right? So then if you want to have a Boolean expression for NOT gate, so we can say Q equals A bar. Complement represent A bar by putting a bar on top of A like this, right? So this is called sometimes A dash as well. So when you want to type in a computer keyboard, you can say there's no bar, so you can use A dash. So both representations are used. So the symbol, now finally we need to represent NOT gate. First you start with a small triangle, and then you put a small circle in front, right? And then we have one input, and then we have one output. If the input is A, we know the output is Q, and Q is equal to A bar, right? So this is how we will represent NOT gate. So as a symbol, we can represent NOT gate like this.